Hi, I'm Don Miley with the Idaho National Laboratory Tours Office. Welcome to the Reactor Technology Complex. What you'll find here in this fence is basically everything that has led up to nuclear power in the United States, beginning with the Materials Test Reactor in 1953, began operating and did the first testing on what materials to build reactors out of, and fuel samples and cladding samples for nuclear reactors. All of the experiments that went into MTR, though, were bolted to the outside of the shielding. It was determined the best testing could be done in the core, and with that led to the development of the Engineering Test Reactor, which began operating in 1957 and had the first in-core test positions. It took over what MTR did, but there was still a better way to do it, and that led to the design and construction of the Advanced Test Reactor behind me, which we'll go visit now. We're now on the main floor of the Advanced Test Reactor, which is right behind me. The Advanced Test Reactor, or ATR, was built in the early 60s, began operating in 1967, loaded with experiments, and at full power in 1969. It's still operating today. It is the most unique test reactor in the world. Let's go take a look at the core configuration and describe why it is so unique and so beneficial to the U.S. Here we are at a drawing of the Advanced Test Reactor, the reactor vessel, where the core is located, and it really shows the enormity of the reactor vessel. It's 35 feet tall, it's 12 feet across, and yet the core of ATR is relatively small. The core is only 4 feet tall, 50 inches across, and it's located towards the lower portion of the reactor vessel. Very compact core. The uniqueness of ATR, why it can do what it can do, comes in the design of that core. And if we look at this diagram, it shows the core with the orange area serpentining around, representing the location of the fuel elements. You'll notice that the four corners and the center are almost entirely surrounded by nuclear fuel. What that allows ATR to do is to generate more neutrons than any other power plant can, sometimes up to 100 times the neutrons that a power plant can generate to age materials, which allows researchers to determine what do we build a reactor out of, what structural components, cladding on the fuels, everything that needs to be known, we can do the testing right here. These locations are also very unique in that we can control the temperature and pressure on that experiment independent of the rest of the reactor operation. ATR is very low temperature, low pressure. Water comes into the reactor at 125 degrees Fahrenheit, exits at 160 degrees Fahrenheit when operating at full power. Inside of each of these locations, though, these 9 locations, we can mimic the plant conditions of any other reactor. We can run coolant over an experiment, externally heat that coolant to 500-600 degrees Fahrenheit, to 2,000 pounds per square inch water pressure or better, and exactly replicate the plant conditions for the reactor we're testing for, which is a very unique capability. Nobody else can do that. In addition to the testing that can be done in these prime locations, these other lettered and numbered holes are other drop-in experiment positions. Not only do we do materials testing for reactor programs, we also conduct isotope production. We generate cobalt-60 for medical applications, iridium for industrial radiography to X-ray welds on skyscrapers and bridges and ship hulls. It's an incredibly versatile reactor. I briefly mentioned the positions of the fuel in ATR, the orange area that serpentines around. Each fuel element looks exactly like this. This is a dummy element that I'm holding, but this is what they look like. And by looking in the end, you'll notice there are 19 plates in each element. Each one of these is made for us by Babcock & Wilcox in Lynchburg, Virginia. It's an aluminum-clad fuel, allowing more neutrons to be generated to impact the experiments. Whether it is the Navy or one of our commercial customers, aluminum-clad fuel will allow that to happen. Our main customer right now is the United States Nuclear Navy. They're doing a considerable amount of testing here to keep the fleet in service safely, better than any other Navy in the world can do it. We also have had customers from South Africa, South Korea, Canada, the UK, France. They've all come here to place experiments in the reactor. So we have a number of different customers, and yet there's room for more. And since the spring of this year, 2007, the Advanced Test Reactor has been designated a National Scientific User Facility, which allows other entities to bring their tests into ATR. universities and colleges that may not have the funding needed to get experiments in the reactor will now be able to bring their experiments here with the cost covered by the Department of Energy and get their experiments here. It will expand the knowledge base for all nuclear research across the country in ways that we have not seen before. Here we are at a model of the Advanced Test Reactor, which shows the layout of the entire plant. As I mentioned previously, it is a very low temperature, low pressure reactor. The water enters the bottom of the reactor vessel through two 24-inch water lines, flows through the core and goes from 125 to 160 degrees Fahrenheit and out through four 18-inch water lines. It then travels to a series of heat exchangers on the other side of the building where the heat is transferred to a secondary water system, which then goes out to the cooling towers, and that heat is dissipated to the environment. Adjacent to the reactor is a transfer canal. Not easily seen in the video, but there is a discharge pipe in the canal that butts up to the side of the reactor. So fuel is manually lifted with long-handled tools, placed into this pipe, which is then moved into the canal area, and operators can then move the fuel into storage racks. Some fuel, after it's been used, will be reused, typically 3 to 4 times before its energy value is completely spent. Once that has happened, it will remain in the canal for a minimum of 1,200 days to cool thermally before it is transferred to the Intech facility for longer-term storage. Let's go take a look at the canal. This is the canal for ATR, where the spent fuel is brought. As I mentioned previously, behind me there is a portion of the canal that butts up to the side of the reactor. It's 45 feet deep right there. That's where the discharge tube is located for the operators to lift fuel out of its position, put in the discharge tube, and brought to this side of the canal. And directly to my left are the storage racks for that spent fuel. You'll notice as you look down into the water, there is a blue glow from the fuel. That's called the Cherenkov radiation effect. A Russian physicist named Cherenkov explained it. You're essentially seeing what will happen when particles exceed the speed of light, which really isn't possible. But in water, when light is refracted and the speed reduced, particles can now exceed the speed of light in that medium. And just like when a plane exceeds the speed of sound, it creates sound. These particles are creating light, and it's in the blue spectrum. The operators are on this walkway across the canal from me, handling the fuel with just long-handled tools by hand. Besides the fuel that comes to the canal, isotopes and other experiments are also discharged through the tube to the far end of the canal. The cobalt-60, the other tests that come in and out of the reactor are moved to the far end. When it's time for the fuel to leave this building, it's been completely used, or for the isotopes to leave, it's relatively straightforward work. A cask, a shielded cask, is placed in the canal. The operators, again with their long tools, will move the experiments or the fuel into the cask, put a lid on it, bolt the lid on, and then lift the cask out of the water, which will then provide shielding. They can then transfer that material to wherever it's going. If it's fuel, it goes to Intech, to longer-term storage. If they're isotopes, they may be shipped to a final customer. At the far end of the canal, it makes another left turn and goes under a confinement door into a square pool where the Advanced Test Reactor Critical is located. It's an exact replica of ATR, but it runs at much lower power levels. That is used for experiments which are unlike anything we've had in ATR before. The operators need to know how those experiments will affect reactor physics. The experiments are placed in the critical reactor first to operate at low power, and then they can build a safety package around that before putting the experiment in ATR for full power operation. One of the features of ATR that you don't see is a containment dome. Oftentimes when we see reactors, we associate a large containment dome over the reactor. In those cases, those reactors are operating at very high temperatures and high pressures, with the energy value that could result in a steam explosion. In the case of ATR at low temperature and low pressure, a containment dome is not required, but a confinement building is, and that's what is over ATR. Keep in mind, ATR is truly a national gem. It's able to do things that no other reactor in the world can do, and it is truly an asset to the nuclear research program for the United States and really for the world.